Hi all, welcome to my YouTube channel Know About Embedded System. In today's video, we are going to discuss very important topic that is called as memory mapping in ARM Cortex processors. Very important in most of the interview, this question already appeared. So how the memory has been mapped for ARM processors, nothing but ARM Cortex processors. So before starting today's video, please subscribe to my channel and gain the knowledge on embedded system. Let us start the video memory mapping in ARM Cortex processor. So what do you mean by this memory mapping in the processor or ARM Cortex processor? So basic fundamental thing is processors will not have any memory. So we all know that already processors will not have any memory. So whenever you want to interface a memory, blindly we cannot interface memory to the processor. There is a systematic and there is a scientific design is available in the industry. Based on that systematic and scientific design, we have to interface a memory to the processor. So that complete process is called as memory mapping for your ARM processor or ARM Cortex processor. So how it looks like. So this is how it looks like. So we have a processor in one end. So this is your ARM Cortex processors, and here you can see this is a memory. So this memory we are going to interface, or the chip designers are going to integrate processor and with the memory. And this memory is totally 4 GB because 32-bit for almost all 32-bit processors we can interface up to 4 GB of memory in this fashion or in this way. So there are different segments are there are different parts are there. Let us explore what are those and let us understand memory mapping. Okay, let us start the video here. So we know that already processors, especially the ARM Cortex based processor is 32-bit processor. We know that already. So when you want to interface a memory to this 32-bit processors, you can maximum up to 4 GB you can interface. And this 4 GB of memory is classified into different parts. And it is classified like this. We'll have a core memory, we'll have a static RAM, we'll have peripherals, we will have external memory, we will have external devices, we will have a peripheral bus, then we will have a system control, and we will be having vendor specific. The same thing you can see here. So code segment 0.5 GB up to 0.5 GB you can interface for the code, nothing but your flash memory. Then we have SRAM, again it's a 0.5 GB. Then peripherals. So peripherals, you know that already. Peripherals includes our UART, SPA, I2C, GPIO, and so on. All those peripherals, it is 0.5 GB, it is reserved. And if you want to interface any memory, so whenever you want to interface any memory externally, instead of apart from this built-in which is available in the memory mapping, whenever you want to interface external memory, for that purpose totally 1 GB is reserved. And if you want to interface any external peripherals other than regular peripherals, for that also it is assigned with 1 GB. And then we have private peripherals related to processors, and then we'll have vendor specific memory. So this is a complete memory mapping of your ARM Cortex processors. So let us explore one by one what is the meaning of each and what is the range. The first one is code. Already I have told you code region is nothing but our code segment. Okay, the code segment is nothing but your flash memory. Most of the time the code memory is nothing but flash, or you can say EEPROM sometimes. So most preferably the flash is going to be mapped into the code memory, and the addressing you can see here, it is starting from 0000 to 1FFFF. Okay, and then 0.5 GB is allocated for this code region. And then second one, here you can see the second one says about SRAM, static RAM. For this static RAM also it is allocated with a 0.5 GB, and in this static RAM, or you can say SRAM, we will be allocating our dynamic memory allocation such as a stack and heap we're going to use. So it is going to hold the volatile data such as a stacks and a heap and your volatile data types and so on. Okay, So that is your SRAM, and you can see the address here. It starts from 2000000 to 3FFFFF. Okay, so this is 0.5 GB for SRAM. Then for peripherals, so peripherals, in what are the peripherals? When I say peripherals, your GPIO, your SPI, I2C, CAN, and so on. These are all the peripherals. For peripherals, totally 0.5 GB is allocated here. For peripherals, it is 0.5 GB allocated, and you can map any type of peripherals within this 0.5 gigabyte, and this is a memory. Okay, and then the next block or a next memory map is your external memory. As I already told you, sometimes in our embedded system application, internal memory may not sufficient to develop our embedded system application sometimes. So in that situations, we have to interface external memory. Okay, so for example, if we have a car which is recording a live video, so in that situation, we have to interface external memory for that in order to record the videos. So in that type of situations, we have to interface external memory. So here we can interface even RAM and ROM both, exclusively external memory. So for external memory, it is 1 GB of data, 1 GB of memory is allocated. The next one is external devices. Similar to the memory, for external devices also, they have allocated 1 gigabyte of memory. 1 GB memory is allocated for external devices, where you can interface external peripherals along with the regular microcontroller peripherals, such as your external input-output devices, like if you want to interface a USB, or if you want to interface external motor driver or motor peripherals, or if you want to interface external CAN device. So in that type of applications, we can interface within this memory. That's called as external devices or external peripheral. For this external device also, it is 1 GB it's allocated. The next important one is called system peripherals. So system peripherals region will start from E0000 to FFFFFF. Here again it is splitted into two parts. Here you can see the system is divided into two parts. One is a private peripheral and one is a vendor specific. So it is divided into two parts, private peripherals and vendor specific. So what do you mean by private peripherals? Private peripherals in the sense the peripherals which are related to our core processors. In our processor also we'll have some built-in circuitry mechanism or built-in peripherals. Those are all called private peripherals. Okay, these private peripherals includes our NVIC, that stands for Nested Vector Interrupt Controller. Then we will have system control unit or system control block, and then we will have data watch points, then we will have a RAM table and ETM, embedded trace macro cell, and then we will have TPU and so on. There are many more things are there, but very few I have listed here. These are all the things which are related to the processor. That is why it is called as private peripheral parts or private peripheral bus. So in this section, you will see all this type of peripherals such as NVIC, control, system control unit, data watch point, floating point, RAM table, and so on. Okay, so then we have final one that is called vendor specific. So name itself says that vendor specific. What do you mean by vendor specific? Vendor specific means this is related to your microcontroller development. So some microcontroller, they wanted to include their own circuitry mechanism or their own peripherals they wanted to map here in the vendor specific. So for that purpose, we will be using vendor specific memory, which is starting from E0 10000 to FFFFF. Okay, so this is called as a memory mapping of your Cortex processor. I told you already, blindly it is not possible to interface any memory to the processor. There is a scientific, there is a systematic process is defined in the industry. According to that, we have to interface a memory. So according to this mechanism, currently what you are seeing on the screen, we have to follow same address we have to follow, or else there will be a memory fault. Okay, or you can say a memory abort, it will happen. Segmentation fault errors, it may occur whenever you're going to violate memory rules and regulations. Okay, So with this, let us move to the one more small topic called as a bit banding. So what is this bit banding? So it's very straightforward definition. This is nothing but bitwise operations. We have all you might have already known that in our embedded system we are going to use bitwise operators, bitwise AND, bitwise OR, bitwise. So along with that, in microcontrollers also there are many bit configurations we will do in order to control or in order to set, in order to clear. So we're going to use a different bit configurations in our embedded system programming. For that particular application, ARM Cortex, they have defined separate block called as bit banding. So what do you mean by bit banding? Bit banding means the bitwise operation. This bit banding process will allow programmers to use bitwise operations. Okay, so for this bitwise operation in the memory mapping part, so totally you can see here, so totally 1 megabyte of memory is allocated for 1 megabyte of memory is allocated for this bit banding. You can see here, this is the space which is allocated for our bit banding, and 1 megabyte and 32-bit length. So 1 megabyte into 32. So just if you multiply, you will get some value. Okay, so that much, those many bits they have defined. So just you try to calculate in your systems 1 megabyte into 32. You can say 32 megabits they have defined. Okay, so those many bits they have defined for our bit banding, and this will help our microcontroller developer to handle bitwise operations in order to control some of the peripherals with respect to the bits. Okay, so let us see what our theory says here. You can see here, so when I say bit banding, I already told 1 megabit of memory is allocated for this bit banding. Okay, and what do you mean by this bit banding? So here you can see point number 3. This is an optional feature which will provide you atomic access of a single bit of a memory by which each individual bit we can calculate or we can do the manipulation. That is what I told you already. The bit banding says that bitwise operation in the memory, and this will help our ARM in order to interact with the different peripherals in order to go for load and store operations. This will allow a single load and store instruction to manipulate a single bit without read modification or without write any modification. So this is again an advantage for our ARM processors. Without taking much time or without modifying a main program or without modifying any other thing, just we can operate directly in the bit level. Okay, and the bit banding, this also will help our microcontrollers, because you know that already our microcontrollers most of the time we will be working in a bitwise operations. So sometimes we will be doing single bit, sometimes we'll be doing 2 bits and so on. So this will help in our microcontroller programming to control different operations. Okay, yeah, so what is the size of each bit band memory? I already told you. So we're going to use 1 megabyte of memory, 1 MB memory, and which is going to be 32-bit in length. 32-bit into 1 megabyte. So totally 32-bit into 1 megabyte bits will be available for our bit banding. Okay, so this is a complete memory mapping. So this is a complete process of a memory mapping for ARM or ARM Cortex processors. Most of the ARM Cortex processors will follow same memory mapping, so there will be no deviations, but there will be slight changes in the peripherals, private peripherals or vendor specific and so on like that. So most of the processors, they will follow same. This is a universal architecture for all 32-bit microprocessors. Okay, so with this I just want to end my video. So if you feel this video is very good, please click on the like button and subscribe to my YouTube channel to know more about embedded system. So let us meet in the next video. Thank you for watching.